Entering. So now how I come back? Do you know what I should push to come back?
Okay, we not. Okay.
At the same time.
Three masks.
So we don't need mask or
I don't know. I think formally we, I don't know.
Uzbekistan one doesn't know what that is.
Just check. Even wrote here state school number 11. 84, right? This is PhD. Postgraduate means 84. That is PhD. What's
I found 3 papers. I found 3 papers, but don't really know from which one it is.
Maybe we can ask the guy tomorrow to provide us.
Yeah.
We don't do anything, and we do even less than nothing. Our contribution will be not zero, will be minus something.
We have to read.
Not even zero.
We pay for the publication.
Exactly. So we provide money.
3 years old.
so bad?
What?
So bad.
So bad what?
You not pay the money. Let's start. So what do I have to do? Grab a mic or what?
No, we have it automatically.
Okay. So everyone who needs. What is this? Is this part of your talk?
Yeah, I try.
Okay.
I think so.
Okay, so then let's start. It's a pleasure to welcome Professor Andrey Kolovsky to our PCS seminar, which is, I think, for the first time since a long time in hybrid format. I see an unusual number of people from this room participate. Let me say a few words about Andrey. He did his PhD studies and PhD in Krasnoyarsk under the supervision of George Zaslavsky, who was together with Boris Chirikov, thank you, one of the founders of chaos, of dynamical deterministic chaos, and maybe then also later even moved also into quantum chaos. And I had also the pleasure, by the way, to meet both of them, great people. And then Andrey continued and did his kind of habilitation or Doctor of Sciences, as it is called, also in Krasnoyarsk some years later. And he spent a lot of time abroad. He was working for almost probably 10 years in total in Germany, in different places, in Essen, in Kaiserslautern, and in Dresden, where we met for the first time and became friends. And then he also worked on the Heraklion at the University of Crete. And he also visited us some time ago before the pandemics hit. And we have a joint publication from that visit from 2017. He's a specialist in quantum chaos, in deterministic chaos, in ultra-cold atomic gases, in driven systems, and maybe in many other things. And I invite you to check his publication list on Google Scholar, which is quite impressive. And today he will talk to us about And I don't see the title, so I just see open Bose-Hubbard model. So I guess I'll take that. You can see. So, please, the floor is yours.
Thank you. So let me begin with formulation of the questions I am going to discuss. And for this, I refer to this figure, which is a scheme of the laboratory experiment which was conducted with cold atoms in the laboratory of Tillmann Hessinger in Zurich. And in this figure, this red surface is essentially the equipotential surface of the optical potential. And cold atoms, loosely speaking, are there under this surface. This scheme was intended to mimic the standard setup in the solid state physics, the so-called two-terminal transport. We have one reservoir of the particles on the left, one reservoir of the particles on the right, and these reservoirs are connected by a lattice. Here the lattice consists of 1, 2, 3, 4, 5 steps. So if the density of the particles, let's say in the left reservoir is higher than in the right reservoirs, we have a current from here to here, and we want to calculate this current theoretically. This is the combination of the problem. Okay, the first step in the analysis is to formalize the problem. And this formalization brings us to these mathematical formulations, where we have one important point, maybe. What is good with cold atoms as compared to the solid state system. So in cold atoms, you can use both Bose and Fermi atoms. So you can consider using essentially the same setup. You can consider the transport of the fermionic carriers, for example, with the rubidium-86, which is fermion, or use rubidium-87, which is bosons. So that you will have both possibility to study the transport of fermionic or bosonic carriers. I shall mainly talk about bosons. But some results can be equally applied to the fermions. Just notice that I have only the Bose-Hubbard, or the Fermi-Hubbard.
Question. So how do you know that which one you can treat it as a fermion and which one you can?
Oh, okay. So cold atoms, they're cold because the experimental works with temperature of nanokelvin's temperature. At these temperatures, the kinetic energy of the atoms is so low that they can be considered as elementary particle. And then the only points which distinguish the fermions and the bosons is the total spin of the atom, which is for the atoms, you should calculate the total spin of nuclei, the total spin of all electrons, and the orbitals moments. So when you sum up all moments, you will get either integer number or half integer number. For example, for rubidium-87, this is an integer number, 1. Then if you remove one neutron from the nuclei, it's 1/2 smaller, and then it will be fermion. It is essential.
Thank you.
What is this?
Someone entered the waiting room and I don't know how to.
Okay, so this is formalization of the problem. So this is left reservoir, this is right reservoir, and it is the lattice. In the cold atom business, when you work with boson or fermions, the lattice, cold atoms in the lattice are very well described as the Bose-Hubbard model, Fermi-Hubbard model. This is the Bose-Hubbard model. Let's say the parameters, I might need to put here also the Bose-Hubbard Hamiltonian. So here you have delta L, which is on-site energy on the site, which is from 1 L, from 1, 2, 3, 4, 5, 6. Sorry. Then you have the interaction energy. So if two bosons share one in the same site, they have to pay energy. For atoms, this is really very well justified because atoms interacts collision-like. So then feel each other only when they are indeed in the same well of the optical potential. So it's very short-range interactions. So this interaction term is very accurate in this sense. If there is only one atom, it's zero. But if you have two bosons in one well, you already have to place the interaction.
May I ask?
Yes.
So this current, how it depends on the length of this chain?
Oh, this is my talk.
I mean, this is what you want to
Yes.
calculate. But at u equals 0, what would you say?
This is also I shall tell.
Okay.
5 minutes. Okay. Okay, and this is hopping, which allows atoms to move from one side to another one. So you see that formally you annihilate the atoms in the L side and create the next side. So this is essentially the hopping. So this is the Hamiltonian. That's all. Yeah, okay. And the next things, the next steps, what we have to do is to eliminate reservoirs and to obtain the master equation for the reduced density matrix of the carriers in the chain, which I know by capital O. It is the reduced density matrix of the carriers in the chain. So this is huge matrix. So for bosons, it's formally infinite. For fermions, it's exponentially large, depending on the system size. But nevertheless, one can obtain these equations by assuming, by making quite a general assumption, which is known in the literature as a Bohr-Markov approximation. In fact, this is two approximations. One is Born approximation, the second one is Markov approximation. The first approximation tells you that if you attach a lattice reservoir, let's say reservoirs, single particle matrix of the reservoir, I shall tell later what it's on, does not change practically. And the Markov approximation essentially is that you can neglect all memory effect. This one. So if you assume that this for Markov approximations, usually they are written using the dash, like one approximation, but in fact this is two. So you get to this master equation for the reduced density matrix. Here is this Hamiltonian, this is reduced density matrix, and the reservoirs are taken into account by the two Lindblad terms. First one is responsible for the first reservoir, and the second one for the reservoir to the right reservoirs. And this is explicit form of these Lindblad terms. So this is for the left reservoir, bar NL. This is the mean particle density in the left reservoir. And physical meaning of this capital gamma is the exchange rate. It's rate at which the reservoirs, at which the particles count from reservoir to the systems or goes out of the system back to reservoir.
And temperature is equal to 0.
Right? No. I mean, here for the moment, no temperature. You will see what is the problem with temperature. I mean, this is just if you assume the Bohr-Markov approximations. How temperature enters in the Bohr-Markov approximation, I shall discuss a little bit later. Okay.
No, but there should be noise term if there is temperature.
You will see it will be there.
But
But for the moment, no temperature. This is what you get by using the Bohr-Markov approximation.
when
And in the literature, all this called the open Bose-Hubbard model.
When the approximation is justified, I will see. Okay, good.
Okay, this is as I say, now it's called the open Bose-Hubbard model. Here, open means that unlike the standard, I mean this one Hamiltonian, the open Bose-Hubbard models does not conserve energy of the systems or number of the particles. So neither energy nor number of particles are integrals of the motion. This is
I'm sorry, in this Hamiltonian HE, you consider only the on-site interaction,
Only
no
on-site.
interaction between the sum.
only one side interaction. And this is a very good approximation for all quasi atoms. They are neutral, it's collision-like interactions.
So if NL equals NR, then you basically have the same chemical potentials, one could say, right? And you won't have any kind of charge or mass.
Yeah, okay,
Right?
yes.
But could you still have, what will control the flow of, I think this is coming back to the question of temperature. Which parameters will control the flow of heat, so to say?
Be patient.
But it should be somewhere.
Not here,
Not
no.
here, okay.
If you assume Born observation, this is all you can get. This is all. Yes, I forgot to mention about this one. It has essentially the same form, but instead of the mean particle density in the left reservoir, you put here the mean particle density in the right reservoir. And the state of the index 1, you should put here index 2, the last side. So this is the status. Okay, so we got this equation. What can this is really standard procedures which you can find in any textbooks on quantum optics, how to do this using the Markov approximations. So then we have to solve it.
You have both particle current and energy current. Is it different?
Here I consider particle current.
What do you mean you consider? I mean, there's still energy involved, right?
Yes, of course. So if there is current, I guess the energy is also involved.
There are two currents.
What I'm interested in is the current, the bus current. Like we charge current with the electrons in there. Okay. You have to solve this equation. So, and fortunately, at least in some cases, we can solve it analytically. In particular, the case of the non-interacting bosons. If this is 0, bosons are not interacting, we can solve analytically and obtain these beautiful results. Beautiful due to its simplicity. So look, the current is given by the difference of the densities in the reservoir. And here is two factors of these forms in the solid state physics is known as the Itzhak-Kitsu relation. When capital gamma is small, it's proportional to gamma.
So where is the length of the chain?
In this case, next slide, okay? Okay, so now you might ask me, so how do we get these results? So the point is that if we have non-interacting bosons, then from this master equation, we can derive the master equation for the so-called single particle density matrix. And this is its definition, single particle density matrix. So unlike the reduced density matrix, which is infinite, this is finite. It is always the same size as the size of the system. And this is the example of the stationary single particle density matrix for perfect lattices. Perfect, I mean that on-site energy are the same. So then this is lattice of the, I guess, 20 sites, 1, 2, 3, 4, 5, yes, 20 sites, 20 sites. So the physical meaning of the diagonals, this is populations of the lattice sites. And all diagonal elements determine the current. So when we calculate these density matrix, we know. So also one can calculate analytically more interesting situation. For example, when you have not perfect lattice, but the lattice with defect somewhere here in the middle. So, for example, all zeros except one in the middle of the range. So you see this, the process of repetition of the scattering, and then you have a kind of specific scattering theory. It is scattering theory, but it is formulated not in the terms of the wave functions, but in the terms of the density matrix. One can also address, for example, the question about Anderson localization in this system. Yes, by using this specific scattering system. So if somebody wants to consider this problem, I am ready to do this together. But all these cases are non-interacting cases. And then comes the main questions. Now I can answer your question about the length. So if you can even see here that there is no difference in the between. So in this case of zero interactions, the current does not depend on the lattice size.
So it means that you are calculating the tunnel resistance.
In this case, yes.
So instead of the lattice, you could take only one side, and it would be the same result. Only your gamma will change, maybe.
Okay, 3 sides, let's say, because so these 2 H sides is slightly different. So if the lattice is larger than 3 sides, the results will be the same.
And what happens if it is only one side? I mean,
If it's only one side, there will be slight difference in the value of the current.
but what would be different? The just value of gamma or what?
No, I mean these equations for the current. Which
No. You had the result in previous slide.
Yes, I can put it here.
No,
That is probably assuming that you
No,
have
the
more than
previous,
two
yeah.
sides.
I can how I can look it up here, but
Oh, the other.
seriously, I cannot.
Okay, sorry.
Okay, I remember the result by heart. I shall.
There is J gamma divided by J squared plus.
So the current, stationary current in the systems is equal to J gamma, J squared plus gamma squared, gamma squared. Yes.
Yeah, so
There is a difference. This equation is valid for n more than or equal 3.
so if L is 1, this equation is not correct. Or something, what?
Not correct.
So how it will change?
This is correct.
Yeah,
This will change slightly.
but how? Gamma will change or what?
No, I mean,
We have no
wait,
functional form.
yeah,
Well, can you tell what it will look like?
No, I don't remember by heart. It feels slightly different. Maybe the PS, this is square plus something else.
We cannot see you on the Zoom.
Don't believe in this.
I think we have a comment from the.
No, because this is resonance tunneling problem. I know it very well. At U equals 0, there is no.
There is. Don't transform this seminar in the Russian seminar.
I can shut up if you want, but no. You want to.
It's also like.
Just as an argument, book, I mean, the first and the last slide has slightly different populations. It means that only the left one. But you have this equation, you have to have at least 3 sides. This is the point. Okay. So what I display this equation. So do we solve the conductivity problem? Of course not, because there are 2 big questions which are left unanswered. The first one, this is the interparticle interactions. And second one is the validity of the master equations. Or like you concluded, is the Markov approximation justified one? Well, now I am going to discuss this problem one by one. Let's start with the fact of interactions. Now look, okay. The battery is low. No.
Yeah, Andrey, one more question. I'm sorry.
Okay.
This delta L, small delta L, nothing depends if U equals 0.
This labels the sides of the lattice.
No. Suppose they are all equal to each other, but different from 0. Delta L.
You mean this one?
Yes.
So this is for the case when all are 0, or let's say equal. And this is the
No, but suppose they are equal to infinity, very, very large.
infinity I didn't consider.
No. Delta L is how it compares with
In
chemical
this-
potential.
Yes, in this model, there is no chemical potential. It appears later on. I show you how it appears, but in these models, this is, let's say, the problem of the Bohr-Markov approximation. You will see where it appears. We come to the chemical potential and temperature in a moment. If we manage to move to the next slide. Oh, beautiful. Okay, thank you. Okay, now interactions. So interactive bosons. There are no universal methods to take interaction into account. I personally use the so-called pseudo-classical approach. If you have time, doubt about this, I shall explain the main idea of the pseudo-classical approach, but for the present moment, it's enough to say that it is approximation to the exact solutions and its work. The pseudo-classical works better the larger bosons we have in the system. Formally, it is exact in the case equal 0, so then it's exact, and if it is not equal 0, then it's exact in the limit bar n, say L multiplied by O. This is constant, but this one tends to 0, and this one tends to infinity. So this is the limit where it's exact, mathematically exact. But when you do numerical simulations, you, for small systems, compare the exact dynamics with what's predicted the semi-classical approach. It appears that it gives quite accurate results than this one of the order of 1. Quite smaller than p.
I'm sorry, can you comment on some situation, which case this the mean value of n goes to infinity in the experiment?
I say about the mathematical results. In the experiment, these parameters are fixed. This is fixed by the nature. This one can be varied by the experimentalist, but also in the limited intervals. In really one-dimensional optical lattices, these parameters of the order of the limit. This is what I tell you that pseudo-classical approach also can capture the situation. Okay, I'm coming to this figure, which compares exactly the case with the interacting and non-interacting bosons. This is occupations of the lattice sites. Of the lattice of the lattice 40 sites. So here is exactly this number, which is divided by L, normalized to the L. So you see that the first site of the lattice has the same occupation number as the density, but as a particle density in the left reservoir. And this, the last site, has the same occupation number as the mean particle density in the right reservoir. And these 2 points are connected by some smooth curve, which is in strong contrast with the case of the non-interacting bosons, where you have equal occupation given by the arithmetic means between the densities of the reservoirs, except the first and the last sites. This is how it looks like. But this is not the main results. The main results is presented in this figure. It shows you how the current depends on the length of your system. So this is the current as a function of this length of the system. And you see that it decreases as 1 over L. So essentially, we have the ohm law. So larger Y is, the smaller the current. This is the ohm law. And again, this is in strong contrast with the case of the non-interacting bosons, where the current is in the middle of the lattice size. And from this, we draw the following conclusions. That
So
when we-
these are experimental data.
all this is the results of the solutions of the master equations.
And then what is this?
Because these are calculated by using the pseudo-classical approach, this is, let's say, some numerical error which can be reduced if you have a high count.
You mean like,
This is not the experimental, this is numerical error.
you mean like Monte Carlo error?
No, it's Monte Carlo simulations, Monte Carlo. Okay, good.
Sorry, but I need a little bit more. I mean, these occupation numbers are computed starting from what? From the solution of
Right, the master equation for the reduced density matrix.
Right, but the reduced density, which dimension? I mean, are you still using the
Formally
one?
infinite. Formally infinite.
Your pseudo-classical approximation makes it finite.
Allows to treat
Kind
the
of.
infinite now. Yes.
Something like a cutoff which you introduced. Is that it? Or is it more than that?
In the pseudo-classical law, there is no cutoff. The cutoff appears if you do the exact quantum calculations, then
You have to do a cutoff. So what's the pseudo-classical approximation?
I come at the very end.
Oh, you can say a few words at least. Okay. I'm not having the dark around. Neglecting some
Yes, of course.
fluctuation.
Of course, yes. No, I better keep it to the end. I want to follow my plan on the seminar.
No.
No.
You actually wrote all these long formulas for density matrix, but you have not wrote the formula for current. Or at least I have not, how current is connected with these L's and R's.
This is proton interaction.
That's the result.
No, you told that you are solving the equation.
Yes.
So how you get current J from solution of the equation, which gives you probably R.
Yes.
So what is connection between current?
Do you want that I have the current operator? I mean,
Yes.
the current is given J is given by the trace of the current operator J multiplied by.
So what is the head?
What is J?
What is the head?
J hat is the current.
Current operator.
Yeah.
We want to see the explicit form of the current operator. Okay. Explicit form of the current operator. J is proportional to sum over L is current total, but usually one normalized to the latest. So this is the density of the current. L plus 1 gamma L minus divided by okay. So from this numerical data, we draw important conclusion that when we increase interaction strength, the ballistic transport, where the current is independent of the lattice size, changes to the diffusive transport, where the current is inverse proportional to the length of the system.
And this distribution is from the condition that current at each site is the same.
Yes, in the stationary regime, the current between the adjacent suns is the same. Okay. There is one open problem. Of course, if you choose increasing corrections, I mean, it cannot happen suddenly. So there is some transitions. The details are unknown. So I especially choose two extreme cases. When you have zero interaction, ballistic response, or pretty large interactions when you have diffusive transport. What is in between, I don't know. Don't ask me this question.
No, but the question is, if U goes to infinity, you think you have diffusion?
This I also don't know. Okay, the second problem. about the Bohr-Markov approximation. So in this approach, we should just talk about the reservoirs is a kind of the black box. We don't know what's there, and we simply say, let's assume that the Bohr-Markov approximation is justified, and then we do the standard procedure and get the master equation.
But I think that's in terms of current operator. I think that you need to have the J. You need to have J in the current operator, the coupling J. Where's the coupling? Big J. The
Capital
coupling J
J.
in your Harmonic
The coupling parameter
here is the current operator.
Here,
Yeah.
yes,
You forgot it probably. Okay.
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 He didn't clean those, so it's proportional.
No.
Yes, it's here, J.
For current operator.
Yes, it's there. Okay.
So reservoirs, they are in both a condensed state or.
Always 2 steps ahead.
It sounds like the seminar at the Landau Institute.
To Israel. It's like.
Okay,
I think it's other.
so but now we want to open this black box to have a control of the Bohr-Markov approximation. So when we open this box, then we find some multi-level systems which possesses the important property of self-normalizations. So what does it mean? It means that if you have some system which you want to call reservoir, then it should possess this property. It should go by itself to the thermal equilibrium, which is characterized by the Fermi-Dirac distributions for fermions or Bose-Einstein distribution for bosons. In principle, we can discuss these models of many body systems. Of course, they are quantum chaotic systems which possess the property of the self-normalizations. But for our present purpose, it is sufficient to consider semi-microscopic models of the reservoir. And this is one of these models. So I attach to my lattice reservoir in the form of the rings with M sides where M can eventually tend to infinity. This is my reservoir, but the property of self-normalizations are introduced by hand by using a number of the Lindblad operator which enforce these rings when they are isolated to relax to the Bose-Einstein distribution. And then we have a full control over the Bohr-Markov approximation. So now I do the same procedure. I eliminate reservoir by rings. And I can completely relax Markov approximation. Just say we don't assume it. It's Markov approximation. Then we obtain instead of the differential equation, integral differential master equations, which looks ugly, but nevertheless it also can be solved in some particular cases. And more importantly, now we describe some effect which cannot be described by the previous equation in principle, in particular the resonance sampling. Okay, and let me give you some particular example. So this will be now for fermions. So I assume that this is fermionic operator for reservoir of the thermic particles. Now each of them characterize 3 parameters: temperature, chemical potential. These 2 parameters uniquely define the density of the particles in the reservoir, but not vice versa. From density, you cannot conclude what is the temperature and chemical potential. But CO2, so then you set the density, and this important parameter is the rate of self-normalization, lowercase gamma. Okay, this is one more parameter, is the coupling between the rings and the lattice epsilon. This is the coupling. Then I come and I example, this one. So then the procedure is again like this one. I consider non-interacting fermions derived from the previous ugly equations, less ugly equation for the simple particle density matrix. Then I consider the case when the Fermi, the temperature is low, so that the fermions in the reservoirs are almost condensed or condensed completely. You have a pronounced Fermi step at Fermi energy. Assume that this Fermi energy almost equal and differs only a small number. And this will be the equation which can be solved analytically. This is density of states of my reservoirs, and I obtain, this is a case of the lattice consistence of four sides, the typical picture for the resonant transmission. So this is the current as a function of the Fermi energy, chemical potentials. When the Fermi energy somehow takes some particular values, I see enhanced current. So this is very a typical topic in the solid state physics. So usually one considers this problem, describe this problem by employing the Landau-Buttiger approach, which in extended versions extensively use green functions. All these calculations produce qualitatively the same results. The difference only is no difference. This is somehow justified by title that it is a solid state physics without the green functions. We obtain the same results not appealing to the Landau-Buttiger equations and green functions. So, but I also want to give you, to draw this color plot. So this is for this line, gamma equal to 0.001. If we increase the gamma, so you see that the resonance, this resonance peak disappears. And this is because when we go in this region of large gamma, in fact, we justify the Bohr Markov approximation in this limit, and this models with ring reduces to the previous model. And the relations with the capital gamma and these two parameters is epsilon squared divided by gamma. How the previous models appears from this more sophisticated model. Okay, this was about all about the resonance transmission. So Basta equation approach is quite sufficient to describe this effect. And now I want to discuss the other class of the related problems. That's what problems which refer to the quantum, the driven dissipative quantum system. So consider the situations when you have, let's say, web reservoirs contains Eisenberg bosons. So let's assume that the web reservoirs bosons are completely condensed. We meet these situations when you have a laser or microwave field. So laser field is essentially the condensed phonons. We attach it to the left end of the lattice, and the right reservoir is completely empty. So it absorbs all bosons which comes through the lattice. And experimentally, this can be realized in the number of physically different platforms. For example, is a list. But this is the platforms which is used chain of transmons, superconductive circuit. So what is transmon? So there is these terms which are also so transmon. It's written like this one. I don't know. It's called this way. Have no idea. But this is essentially the Judison junction-based quantum nonlinear oscillator. For theoreticians, I guess it would be enough. And here you see the chain of the 99 transmons So you put signal, microwave signal from the first transmon and read the output from the master.
But wait a second, this is very interesting, complicated, but if I just consider laser beam propagating through the diffraction grid, is it something different from this?
Well, in diffraction grid, you also want to consider it's like the lattice chain.
No, it isn't. It's a lattice.
True. The only difference is that in these setups, you have no interactions between photons. And here I have interactions between the photons, so I have this interaction terms.
No, but in polaritonic systems.
Yes. Okay, but mathematically, I mean, you have the situations like this one, that now the left reservoir appears as an external driving in the Hamiltonian, in addition to the Haber Hamiltonian, and to take into account the absorptions of the bosons by the measurement device, you add to the master equation the Lindblad term, which has, let's say, the same structure. Well, as you see, it is the same conductivity problem. Well, it's not the whole machinery can be used also for studying this problem. And maybe here I come to the problems which was asked about the pseudo classical approximation. It is simple to explain in this example. Or I will simplify myself and consider the Bose-Haber Hamiltonian consisting, the lattice consisting from a single side. If you consider the Bose-Haber Hamiltonian with single sides, so there is only this only is this frequency and these interactions, and that's all.
I'm sorry, just a curiosity. Is there any origin regarding this transmon? If you just consider the linear as the resonator instead of the non-linear transmon, is there any difference in calculation?
Yes, of course. Okay. The problem is when you have the nonlinear oscillator. With linear, you can do everything. You immediately get the resonance peak, resonance transmission at some frequencies. That's all you have. Okay. So, paradigm example of the quantum, of the classical first and the quantum dissipative and driven system. This is nonlinear oscillator subject to the external driving plus friction. This is the classical problem. Of course, everybody knows the textbook example allows the driven dissipative harmonic oscillator. Then it responds on the frequency of the same frequency as the driving frequency. The interesting thing with nonlinear oscillator is that it, in some region of the parameters, it has stability, which is the origin of the hysteresis. This you can read in the Landau-Lifshitz in the first volume. I don't remember the page, but this is written here. I mean, these problems of the driven dissipative classical nonlinear oscillator. If we use the modern language, it means that in this case, the systems has two attractors, two limit cycles. One is inner attractor and the other is the wow. To say where we come, so for this you need to consider the basis of the attractor. And this figure shows the basis of the attractor. So if we choose initial conditions in the blue area, so the system comes with attractor. If we choose the initial condition in the red area, the system comes to the upper limit cycle. This is two attractors which can go. As I say, this happens only in a certain regions of the difference between the driving frequency and harmonic frequency. So later, but it happens. bit modest. But we want to consider the quantum dynamics. This is also was done quite long ago, I guess somewhere around 1990s, by people from New Zealand. Bose, so if you want to now have the driving, it is not a problem. You introduce the driving terms in the quantum Hamiltonian, and to introduce this equation, you simply attach to your quantum oscillator a reservoir. Or let's say exactly the same term like written here. Now you can omit the index 1 because we have only one side. And also an L you can omit. Every this one, so on, everywhere. This is what you have, and what is written here is exactly these two, 1, 2, 3, 4, 5, 6, 7 terms rewritten, rearranged the different ways. This one from 1 I put here, and this is I read in this form. What is that? Why? Because in these two terms have different physical meaning. As you will see later on, this term is responsible for diffusion, which you cannot avoid in the quantum case. And this one term is responsible for friction. And how we solve this?
And where is pumping? You don't have pumping.
Something where
In the Hamiltonian.
No, what? This is.
Here. Oh no, it's opposite direction. Quantum Hamiltonian. Well, what is the classical approach? You, instead of the master equation for the reduced density matrix, obtain the Fokker-Plan equation for the classical distribution function. How you do this? You begin, for example, with linear functions. Using the density matrix, you make the vector summation and obtain the linear function.
So you are considering only coherent pumping.
Linear functions. You obtain the linear functions, then do the whole stuff. And linear function will be a function of two canonically conjugated classical variables, A and A. And obtain the equation for the linear function. And it will look like this one. First, you have the force on brackets. This is Hamiltonian evolutions. Then the terms which I denoted like diffusion in the previous slides come to this one. And now you see that it is diffusion, it is second derivatives. The terms which I call frictions comes into this stuff. This is the frictions. And I threw away the terms which has the derivatives higher than 2. Like the F. That's all the way. In the literature, at least in the single particle quantum mechanics, this approximation is known as the truncated linear function approximation. But I prefer to use the pseudo-classical approach because you can come to the same equations starting not from the linear function, but for example, define the Husimi function. And also obtain equation for Husimi function and then throw away some terms. So anyway, it can be immediately shown. This is one important thing. This is diffusion term. Look on it. So it's given by this constant gamma, which appears here, and number, the number of the particles in the reservoir. And you see from equations that even the number of the particles in the reservoir is 0, the diffusion term is still present. You can call it irreducible quantum population. And this is very important term because, for example, it does not allow the quantum oscillator go below its ground states. So the ground states with the minimum energy, and it is ensured that oscillator never goes below by presence of this diffusion. And the more importantly, that this diffusion terms also restricts the contributions of the terms like this one. So it will be proportional to 1 or so it doesn't allow these terms to grow. And this is big difference between the open and conservative systems. In the conservative systems, this term can grow exponentially. The chaotic systems here, it's always restricted. So there is really, I mean, you can look more attentively and see when this approximation is justified. Okay, anyway, you obtain these equations and solve it in the case when you can solve it. And you cannot solve it analytically. There is a simple Monte Carlo method. This is a Fokker-1 equations, and it can be mapped to a Langevin equation. And this is the method.
Andrey, I'm lost a little bit. If nu is not in resonance with omega, will it still go to infinity without dissipation?
So situation, it can go in this simple problem, no, but in the other problems, it can go to infinity with chaotic dynamics. If the system, classical system has a positive Lyapunov exponent, it goes to infinity.
So in this case, in this approach, you assume that this symmetric doesn't depend on the position in the link.
Say again. What doesn't depend on what?
On the position of the atom in the link.
In the lattice. No, I am now consider a single side lattice. This is one oscillator, only single side. This is only one oscillator. I simply want to tell you, I mean, the ideas of the pseudo-classical approach. This is all. But this arrow bar comes from that. For the problems we consider, we cannot solve this equation analytically, use the Monte Carlo simulations. For this you need to average over this white noise and averaging ensemble sound defined arrow bar. This is numerical. This one. But here, I mean, the system is good enough to compare, I mean, the exact, it can be solved exactly in the computer, I mean, to simulate the master equation exactly, and use the pseudo-classical approach. And you may see when pseudo-classical approach gives right results. So I put here now is a Hamiltonian H one constant, and like as theoreticians, we can change H bar. So I start with the H bar equal to 1. And if I start with the H bar, then the results is given by this blue line. This is the number of the photon bosons in my quantum nonlinear resonator as a function of the detuning. Detuning is the difference between nu and omega. You will see that it has a peak structure. The spec simply shows you these transitions, 1 to 0 transitions. When you go to smaller H bar, like 1/2, you will see the multi-photon transitions, for example, this peak. This is these transitions. Go and give it to smaller H bar. This is blue line. So these peaks are slightly disappearing and then disappear completely. You have some smooth stroke. This is for H bar 1/2. It means that you see that I put here the mean number multiplied by the H bar. This is of the order of unity. It means that the system has an average 8 bosons. So 8 bosons is quite enough. I mean, this dot is perfectly described by the pseudo-classical approach. Starting from this moment, the pseudo-classical approach to produce all results for smaller H bar. Still, this is not the classical results.
But what is real dimensionless parameter? H bar is not, no, it has units. Here you have, omega nu, capital omega.
Yeah, I do like the theoreticians. If you don't
No, theoreticians.
Okay. So for the experimentalists, so I tell you them what to do if you want to change H bar, effective H bar. So you scale the driving amplitude as amplitude divided. I mean, you use a scaling.
By the way, what is gamma? What is 0.04?
This is
No, small gamma.
It's capital gamma in this case. Thank you. Okay, you use the scaling. Omega, this is amplitude driving frequency, is amplitude of the driving force. You scale as omega divided by C. And you scale if you are experimentalist. You scale the nonlinearity as H bar. So small nonlinearity, large driving frequency. This scaling is good that it's leave the classical dynamics.
So it's basically capital omega divided by U. Yeah, or U divided by capital omega.
Okay, this is a scale.
Yeah. So a small H bar corresponds to what? To small omega.
To large omega driving frequency and smaller nonlinearity. And this scaling leaves the classical dynamic invariant. One big change on the dynamics. For H bar of the order of unity, you have these results. For H bar 1/16, you have these results. Okay, this was all about the pseudo classical approach. And let's say I am afraid that I overloaded you with information. So sorry for this. What should be left? I don't know. That I address the transport, the problem of conductivity by using the pure approach, which is typical for the quantum optics, and try to show you that one can get essential results without appealing to P functions and some Landau-Whittaker theory, and so on. Okay, thank you.
Andrey, for this talk. We had lots of questions, but I guess.
Yes, you have a lot of very few.
So if there are questions, shoot.
Yes. Can you, like, if I don't ask too much, can you tell me how you do the pseudo classical approach for the lattice?
Causalitics.
Yeah.
Oh, this is the same. So look. In the case of a single oscillator, oh, okay, here it is. There is no index L. I have only one differential equation, stochastic one. So if I have L sides, I have L coupled stochastic differential equation. And if, for example, I want to calculate the single particle density matrix by using this approach, I solve this equation for every realization of the white noise.
If you want a new page, you just press plus there.
Do you want a new page? Oh, no, it's okay. Okay. So then I can calculate a single particle density matrix, which is size of the L, simply by here T as AL T. AM T, and then you have brackets denotes use the error ratio or different stochastic realization. So this is the way how I calculate the figures like this one.
Okay, more questions?
Okay, I asked too much, but if there is nobody else. In the very beginning, you had a problem of two reservoirs and this chain between them. And you road current, which is proportional to a difference in density.
Yeah.
But if we are speaking about bosons, you can imagine that in both reservoirs, bosons are condensed. Then it's like a Johnson junction. So there would be also current proportional to phase difference. And the question is how you would include this, at least in general, in this scheme of calculation.
So, okay, good questions. I can think, but of course I cannot. I understand. So you want to attach the both end of the lattice reservoirs with condensed bosons. Maybe tomorrow.
No, because you introduce temperature, assuming that bosons have just usual boson distribution. But if there is condensate and excitations, it would be more rich.
Okay, more questions? Maybe from the Zoomers. Any questions? I'm not sure. I don't see. Actually, there are any.
No Zoomers.
Yeah, sure.
Okay, unmute yourself if you have questions. Otherwise, we will ignore you. Okay, more questions?
Do you see mode insulator in numeric? Do you see mode insulator phase in numeric?
What insulator?
Oh,
What insulator?
What insulator? Well, you see the problem of the superfluidity mode insulator. This is a question about the ground states of the isolated system, let's say.
But your 1D chain have to have a mode.
Yeah, the correct formulation would be really what happens if I increase you. Yes, you.
But can you see that in numeric?
I don't try to do this. So I restricted the case to observe this transition from the ballistic to the diffusive transform. Perhaps if you increase U further, then the current will drop. You have kind of the transitions.
So can I have any comments about the question? When you consider this version of the Josephson junction with the condensate, in this case, your lattice side actually describe the boson, and but in this Josephson junction, then with the type 1 model is well known. You can easily calculate the ground state Josephson current with the Fermion. Then do you expect any some difference when you replace this Fermion operator?
Oh, this Fermions, I am more experienced with bosons. So Fermions, I don't know. It's concerned the Josephson junctions. I simply consider the Cooper pair as the bosons. And for me, the Josephson junctions, and this is two sides, but they have
Pairs are not bosons. It's in BC limit when you form molecules, then you have bosons. But in BCS limit, it's different calculation because excitations are fermionic.
Okay, yes. Okay. Oh, I am sorry. I have never worked with fermions in these directions. These bosons. Then the Josephson junction, as I say, this is two sides, but they have
So in your case, you've just taken U impulse, right? Interaction is impulse.
Here, I consider impulse. In transons, in fact, it is attractive. So the spectrum, not divergent, but convergent. But this is also independent of the side of the interactions.
Now, I have a question again about this current issue here. So you consider the charge current, right? But there is also an energy current. You can also define an energy current, of course. Now, you didn't do this, okay? But if you do this, then my question again is, what are the parameters coming from the reservoirs which will control the energy current? Because we know that we can prepare your Hamiltonian system at two different temperatures, but at the same average particle
Yes.
density. So there's
Yes.
so
You can consider the situations where the chemical connections are the same, but the reservoirs have different temperatures. Then there will be a
So-
current.
so where is this temperature hidden?
I always, I consider, the heuristic might help by considering the case of the temperature for both reservoirs are the same. But it is not a problem to consider the situations when the temperature is different.
Okay, thank you. More questions? If not, then let's thank the speaker again. Thank you. And I guess we expect some food today. Tinan, how do we see whether there are people asking questions? You see them? Yeah, but not- yeah.
You would see it there.
No?
We would see